Good morning, gentlemen. Today is Tuesday, March the 17th, St. Patrick's Day. Top of the morning to you. I hope that you guys are all well and not doing anything foolish. Please excuse the sound of my voice. I've got myself a little hoarse from being outside and running around with my kids yesterday. So just excuse the sound of my voice, and hopefully it won't sound like I'm hitting puberty today. In any event, today's mission is to go through the tools that I'm going to be trying to use to teach you over the course of the next week, and hopefully not much longer than that. But we're going to redo or revisit the lesson on energy and work that we've already. This will be a review, and some of you may be bored with this. But again, this is more of a test to make sure that we're all on the right page and the same page and the right track to make sure that we're going forward with this remote teaching silliness for as long as we have to. In any event, I'm sitting here in our classroom. Hopefully, you can see the stuff on the shelves behind me. The few light bulbs that actually work are on in the background. But what I want to concentrate on today is this idea of work and how it relates to energy. We use the word work in colloquial English in a variety of different terms. We say that we have homework. We say that we have to go to work. We have work to do, blah, 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 blah. But in terms of physics, work is a very specific kind of thing. And it is defined as being done on an object whenever a force displaces that object. And if there's no movement, then there's no work. So if I apply a force to a ball and I push it across the screen, that means that I've done work on that object. The force is applied, and I've done, and it's moved across the screen. Therefore, I've done work. If I apply that same force to a wall and the wall doesn't move, then no work is being done. And so work is only done on an object when a force displaces that object. No movement, no work. Therefore, the formula for work, which is given, by the way, with a capital W, and you can see that here on the bottom of your screen, capital W equals force times displacement. That formula is found on your handy-dandy little New York State reference tables, so please make sure that you check those out. The units for work are given in joules. Joules are named after the famous French physicist Joe Joule and are given with a capital J. And a joule is defined as when 1 Newton moves an object through 1 meter of displacement. All right? So 1 Newton of force moving an object 1 meter gives us 1 joule of force. Okay. Now, that brings us to our first example problem. Hopefully that works. Maybe not. There we go. So, well, thank you, Jesus. Example number 1 tells us, or asks us, how much work is done in slowly lifting a 5.00 kilogram box from the floor to a height of 1.20 meters. All right? How much work is done in slowly lifting a 5.00 kilogram box from the floor to a height of 1.20 meters? Okay? Well, in order to do an example like this, we start, of course, by making ourselves a laundry list. All right? And so again, let's look at how to do a physics problem the way that we've been doing it all along. For example number 1, which says, how much work is done? So the first thing I'm going to do is add W equals big fat question mark to my laundry list. So how much work is done in slowly lifting a 5.00 kilogram mass? So next thing on my laundry list here is going to be a 5.00 kilogram mass. From the floor to a height of 1.20 meters. And so the next thing on my laundry list is here, delta y is going to be 1.20 meters. I'm going to start here by trying to figure out the formula W equals F times D, where the force is, or the work rather, is equal to force times displacement. But what I have to realize is that my force in this case is the weight, because if I'm lifting an object upward, the force that I'm working against is the force of gravity, which is the weight. And so force equals W equals M times G. Well, the mass is 5.00 kilograms. The acceleration of gravity is 9.81 meters per second squared, and if I multiply them, I get 49.0 newtons, 0.5 newtons as my force, right? The force of gravity that I'm working against. Now, if I come up here in the upper right-hand corner and I look at the formula for work, work is going to equal the force times the displacement. And so the force is 49.0 newtons. I'm sorry, I did that again. 49.05 newtons multiplied by the displacement, the height that I lifted up, as 1.20 meters. And that gives me 58.9 meters as my, 58.9 joules rather, as my force. Now, what happens if I apply that force to an object, but I don't apply it in the same direction that the force is being moved? All right. Good examples of this are pulling on the rope that's attached to a sled, or pulling on the handle that's attached to a wagon. All right. In this example, if you look very carefully, this thing represents a wagon, let's say, and I'm applying a force at an angle to the horizontal. I'll call that angle the angle theta. What that means is that the component of the force that actually applies or does work on it is going to equal F sub x, the x component, which is F times the cosine of theta, where theta is the angle between the horizontal and the force that's actually applied. What that means is that the force I'm going to use to do work is going to be F times the cosine of theta multiplied by this displacement, which is delta x. And so the formula that I'm going to use is going to be applied at an angle to the horizontal. All right, and so the work done is going to be given as capital W equals the force times the cosine of theta, which is really just the x component of force, times the displacement that I move. So W equals F times the cosine of theta times delta x. Now, this formula doesn't appear on the reference tables, but remember that the cosine of 0, which is the angle if you're pulling at a horizontal displacement, the cosine of 0 is 1, and so F times 1 just gives you F. And so it really is the same formula that you see on your reference tables. So W equals F times the cosine of theta times delta x. That brings us to example number 2. A 600 Newton force pulls a 50.0 kilogram block a distance of 2.00 meters along the floor. The force acts at an angle of 37.0 degrees to the horizontal, and you're asked to calculate the work that's being done. All right, so again, we're going to make ourselves a laundry list. A 600 Newton force is going to be given. So we've got a 600 Newton force. F equals 600 newtons. Pulls a 50.0 kilogram block. And so the mass of the block itself is going to be equal to 50 kilograms. A distance of 2.00 meters along the floor. So the displacement delta x is going to be 2.00 newtons. The force acts at a angle of 37.0 degrees to the horizontal, and you're asked to calculate the work done. Now, in this case, the mass is absolutely irrelevant, okay, because I'm giving you the force of 600 newtons. So we apply the 600 Newton force, we multiply that by the angle, the cosine of the 37-degree angle, and that by the displacement of 2.00 meters. If you do the arithmetic there, 600 times 2 is 1200 times the cosine of theta, which is going to be a little bit over 0.8. And if you do all the arithmetic there, you get a value for work, capital W, of 958 joules. All right, that may round actually to 559. I'm not absolutely certain, but that is the answer to our question here. Okay. All right. Now, for homework tonight, I would like you to go through and try the questions numbers 1 through 3. I've uploaded the homework sheet onto Blackbaud. Go ahead and look at the topics page in Blackbaud. This will give you the video, the homework sheet, and any other things that you will need in order to carry out our little mission today. Good luck, God bless, and may the force be with you.